So welcome to the last lecture of this course. So I hope you feel that your time has been well spent and that you've learned something useful about transistors. Unit 5 was some additional topics, somewhat miscellaneous collection of additional topics. And what I would like to do is just quickly go through this set of topics that we discussed in Unit 5. The outcomes that we sought here, first of all, we wanted to develop an understanding of the fundamental limits of MOSFETs. MOSFET dimensions have shrunk down for many, many years. We're beginning to approach those limits, and we wanted to develop an understanding of how close are we? How far have we to go? We also wanted you to be aware that MOSFETs are used for other applications besides digital logic and analog or RF circuits. MOSFETs are also very important in power electronic applications. So we talked a little bit about power MOSFETs. Now, there are other kinds of transistors. The silicon MOSFET is not the only type of transistor. We briefly described a transistor called the high electron mobility transistor. So this is a field effect transistor. It's a barrier controlled transistor, just like a MOSFET. And we wanted to understand the similarities and the differences of these HEMTs and MOSFETs. Now, there's a bipolar transistor as well. A bipolar transistor is sometimes thought of as an inherently different type of transistor, but that is not the case. Bipolar transistors also operate by controlling energy barriers with voltages applied to the terminals, and we developed an understanding of how bipolar transistors operate and work, and how they are different from field effect transistors. And finally, we said a few words about compact models for circuit design and how the MVS model that we've been using as our guide throughout this course differs from an industry strength general purpose compact model for design. Okay, so on the limits of MOSFETs. We did it by thinking about the simple energy band diagrams of MOSFETs. In the off state, there's a high energy barrier. In the on state, we push that energy barrier down, allows electrons to flow from the source into the drain, where they shed their energy and stay, and that's a switching event. So we use that simple picture to try to understand what's the ultimate limit of the channel length, how short can we make the channel, what is the ultimate speed? How fast can we switch from an electron from the source to the drain and basically convert a 0 to a 1 or vice versa? And what is the minimum energy dissipation needed to do this? Well, we went through some simple arguments. I'll just give the results here. The minimum switching energy is kT log 2. We developed that from a specific device, a MOSFET, but there are some very general thermodynamic arguments that people use in order to establish precisely the same limit. We established a limit for the channel length. Basically, we said the channel length has to be long enough so that the energy barrier is thick enough under off-state conditions so that the electrons can't quantum mechanically tunnel from the source to the drain. Otherwise, the device is not off when it's supposed to be. And we put in numbers assuming an effective mass of 1 times the electron rest mass, and that turns out to be a very small number, 1.5 nanometers. And then finally, we asked, how fast can we switch a transistor fundamentally? And we developed this simple expression and put numbers in, and that is about 40 femtoseconds. If we look at a reasonably close to state-of-the-art technology today, 22 nanometer CMOS, and put numbers in, you can see that the energy in the MOSFET is 1/2 CV squared. That turns out to be 1,200 times the minimum, fundamental minimum limit. So not that far, only a few orders of magnitude away. The channel length, 22 nanometers, that's only 15 times the absolute minimum channel length, the fundamental minimum channel length. That's relatively close. And the switching speed, in a modern day technology, we would just take Seagate VDD, that would be the charge in the gate, divided by the on current. And that would tell us how long it takes to pull that charge off. We find that it's about 11 times the fundamental limit. So in terms of speed and size, present-day MOSFETs are approaching quite closely some really pretty fundamental limits. In terms of energy, we're still a long ways from that. Part of the reason there is that we need to use larger voltages and dissipate more energy than is fundamentally necessary because we need noise margins. We need circuits that operate in the presence of noise. Okay. Now, in reality, we're not going to get all the way to the fundamental limits. There will be technology considerations. Series resistance is getting more and more important as we scale dimensions down. Parasitic capacitances, as we push everything closer and closer together, the intrinsic gate capacitance is a smaller fraction of the total capacitance. There are various leakage currents from band-to-band tunneling and things, and these practical issues will end up dictating how close to the fundamental limits that we can get. But the point is, in terms of a couple of these parameters, we're very close now. The other one, it's going to be hard to get significantly closer just because we need these circuits to operate in the presence of noise. Now then we switched our gear to completely different applications. Semiconductor devices can be used for power switching applications, and there are a set of low voltage applications and a set of medium voltage applications that are getting more and more important as we go to autonomous vehicles, electric vehicles. And there's a set of really high voltage applications. And semiconductor devices, transistors, and diodes are playing a larger and larger role in these kinds of applications. These quite different applications than our traditional digital logic and analog RF. We talked a little bit about a power MOSFET and what the main considerations are there. We would like it to conduct high currents. We get a lot of current by having a lot of width to the MOSFET, but we would like it to be able to sustain high voltages before it breaks down. And in order to sustain high voltages, you have to spread things out over a long distance to lower the average electric field so that the semiconductor does not break down. So to achieve those goals, power MOSFETs have adopted this kind of cellular design and vertical flows. So the cellular design allows us to wrap a lot of width in a small area. The vertical flow allows us to have large distances that sustain large breakdown voltages. By the way, this sketch is not to scale. The vertical dimensions are much larger than the horizontal dimensions. We discussed briefly the operation of a diffused MOSFET or a DMOSFET power device. So in this device, the two source terminals are on the top. The drain terminal is on the bottom. The gate is right here. And the P-type regions, the blue P-type regions there are the channels of this N-channel MOSFET. When we apply a gate voltage and turn the channels on, current flows out of both sources and then flows down into the drain and out the bottom. Now, if you look at this structure, let's say it's in the off state and no current is flowing. Well, then we have a P plus layer here, a lightly doped N region here, and then a heavily doped P region on the bottom. This is what people call a PIN diode, or very similar. P-type, almost intrinsic, and N-type. So we can use these if the vertical dimensions are long enough. They spread the voltage out, lower the electric field, and give us a higher breakdown voltage. We went through that analysis, and we found that there is a fundamental trade-off for these kinds of power transistors. There's a trade-off between the on resistance. When the device is on, switched on, we would like it to be an ideal switch with no resistance. Well, in a practical switch, we'd like the on resistance to be as small as possible. But when the switch is off, we'd like it to be able to withstand as large a voltage as possible before it breaks down. So there is a fundamental trade-off between breakdown voltage and on resistance. If we want a high breakdown voltage, we're going to have a higher on resistance. But that is material dependent. So silicon power devices are widely used, But if we go to semiconductors that have a wider band gap, like silicon carbide or gallium nitride, this is where a lot of the action is on technology development these days, because they have a much more favorable on-resistance breakdown voltage trade-off, and we're able to move to higher voltages and still maintain acceptable on-resistances. Well, then we switched gears again and talked about a different kind of transistor, a field effect transistor, but a different kind of field effect transistor. This transistor, first of all, it's made out of 3-5 semiconductors. 3-5 semiconductors typically have very high electron mobilities. That's desirable for a transistor. The transistor is called a high electron mobility transistor because that's its main feature, and the main reason for using it is that the electron mobilities in the channel are very, very high. They're sophisticated structures which look quite different from silicon MOSFETs. They're built with heterojunctions of different types of 3-5 semiconductors with different types of band gaps. The channel of this particular transistor is right here. It's sandwiched between two wider band gap layers, and the charge flows from the source to the drain in that small band gap channel, in that quantum well that it is confined in. Well, how do we get to high mobilities? Well, we rely on a technique called modulation doping. Normally, if you want, in order to make a good transistor, we need, and have high currents, we need a lot of charge, and we need the charge to move fast, which means we need a high velocity. But if we dope a semiconductor to get the high charge, we will lower its mobility, and that's not desirable. Well, it was discovered some years ago that there's another way to get electrons into a semiconductor. That is, if we dope a wide bandgap semiconductor and put it adjacent to a smaller bandgap, the electrons will spill over into the smaller bandgap semiconductor. The smaller bandgap semiconductor is undoped, so it has a very high mobility, but now it has a large number of carriers, so it can carry a large number of large electron charge, but those carriers have high mobility. That's called modulation doping, and that's the key feature of a HEMT, a high electron mobility transistor. So you can see the motivation for doing this. A gallium arsenide MESFET is another type of field effect transistor. This is the first type of 3-5 field effect transistor that was used. So there's an N-type source and drain, and there's an N-type channel. And then we have a metal gate that depletes the channel. It's a Schottky barrier. So by changing the voltage on the metal gate, we can change how much we deplete the carriers, and we can modulate the current. And that's how a gallium arsenide MESFET works. Now, if we're making this out of gallium arsenide, pure lightly doped gallium arsenide has a very high electron mobility, 8,500 centimeters squared per volt second. But to make a device like this, we have to dope the channel, 10 to the 17th or 10 to the 18th, and then we lose the high mobility of that intrinsic material, gallium arsenide. So it's this modulation doping concept that allows us to get the carriers we need, but to retain the mobility. So for high transconductance in RF applications, for example, we need both that charge and the velocity, which means we need a high electron mobility. I'll also point out that this device has a disadvantage. The Schottky barrier gate, there's no insulator between the gate metal and the semiconductor. So if we forward bias that Schottky barrier gate, too much current will flow from the gate into the semiconductor, and that limits the gate voltage that we can put on this transistor. So just to summarize, HEMTs are important. It's an important technology for very high frequency RF applications. Both HEMTs and HBTs, which we talked about next, have achieved very high speeds, terahertz speeds, so they're useful for very high frequency amplifiers. HEMTs operate in the same way as MOSFETs do. They are barrier-controlled devices. So the virtual source model can describe a HEMT just as well. In fact, in the 2 lectures ago, when we analyzed measured data, we applied the virtual source model to a HEMT. and extracted some information on transmission and apparent mobility and injection velocity and quantities like that. What we learned from that analysis that we did on HEMTs is that high electron mobility transistors operate at essentially the ballistic limit. Silicon transistors are closer to 60% or so of the ballistic limit, but HEMTs operate essentially at the ballistic limit. So these are ballistic transistors. Well, then we switched gears one final time, and we talked about a different kind of transistor, a bipolar junction transistor. So these transistors, as I mentioned, are frequently thought of as intrinsically different from field effect transistors, but they really aren't intrinsically different. So it consists, if it's an NPN, which is analogous to an N-channel MOSFET, it consists of an N-type emitter. That's like a source. It emits electrons. The source in a MOSFET is a source of electrons. It consists of a P-type layer we call the base, simply for historical reasons. In the first transistor, the base was the thing that held the whole transistor up. The base is sort of like the channel for our MOSFET. And then there is an N-type collector, and that is analogous to the drain of the MOSFET. Now, if we apply a positive voltage to the P-type base, we pull all of the energies down, and we forward bias the emitter-base junction. That's sort of like applying a gate voltage. That lowers the energy barrier between the emitter and the base. And that makes it easier for electrons in the emitter to hop over that barrier and get into the base. And you can see how similar it is to a MOSFET, where the gate voltage pushes the barrier between the source and the channel down, and then the electrons can hop over that barrier into the channel. So the electrons are injected from the emitter. It emits them into the base when we forward bias the base emitter junction. And if we reverse bias the collector base junction, we pull the energy down there, then the collector operates to collect those electrons. They diffuse across the base, and then they go down the energy. They're swept out by the high electric field there, and they exit the terminal. So you can see that this is a barrier-controlled device, very similar to a MOSFET. Now there's one difference, and that's current gain. So the device itself, we lower the energy barrier. We inject electrons from the emitter into the base. They go across either ballistically or they diffuse across, and they enter the collector, and they are collected and swept out by the high electric field, much like a silicon MOSFET. Unfortunately, when we forward bias the base emitter junction, we also inject holes from the base into the emitter. That's an undesirable current. That leads to a current in the base terminal, which would be analogous to a current in the gate terminal. We'd like that current to be as small as possible. So that finite current on the control terminal, that is a distinct difference between a bipolar transistor and a MOSFET, although these days MOSFET insulators are so thin that they have some leakage current. Well, the ratio of these two currents, the current that we want, the electron current in an NPN bipolar transistor, and the current that we don't want, the hole current or the base current in this, the ratio in the active region is called beta. And with some simple p-n junction physics, we could develop a simple expression for that beta that related the beta, the ratio of those two currents, to the ratio of the dopings in the emitter and the doping in the emitter and the base, to the ratio of the diffusion coefficients in the emitter and the base, to the ratio of the thicknesses of those regions, and also to the intrinsic carrier concentrations. Remember, we've been using Ni is equal to about 10 to the 10th in silicon, but it is possible in some flavors of bipolar transistors to use semiconductors with different band gaps and therefore different intrinsic carrier concentrations. The IV characteristics of a bipolar transistor look similar to the IV characteristics of a MOSFET. So we have these same transistor-like characteristics because the internal operation is very similar, manipulating energy barriers with voltages that we apply to the terminals. So each of those curves represents a different current that we squirt in. We could represent each of these as a different voltage that we apply between the base to the emitter, but the currents go exponentially with emitter base voltage, so it's more convenient to plot, to fix the base current and to represent each of these currents as a different forward bias on the base emitter junction, which gives us a different base current. Okay. So this region that we call the saturation region of a MOSFET is called the forward active region of a bipolar transistor. We forward bias the emitter base junction to inject electrons from the emitter into the base, and we reverse bias the base collector junction to collect electrons that diffuse across the base. And then a key parameter is the ratio of the collector current to the base current. If we plot the collector current versus the base emitter voltage on a log plot, this is sort of like plotting the log of the drain current versus the gate to source voltage. And we'll get a characteristic that will look much like a MOSFET. One important difference is that we have 60 millivolts per decade. We have ideal subthreshold swing, even to very large currents, right? There's no real concept of a threshold voltage. If we do go to very high voltages, which give us very high currents, the curve will start to roll over. That looks a little bit like an above threshold MOSFET, but it's simply a result of the voltage drops. Due to these high currents, the voltage drops in the series resistances, which reduce the voltage that actually gets into the junction and forward biases it. Okay, so series resistance is important for these. Now, what is the fundamental difference between a MOSFET and a bipolar? Most circuits are made with MOSFET technology these days because it is the lowest cost, highest volume manufacturing technology available. But we do use bipolar transistors because for certain specific applications, they have some advantages. Those applications tend to be high-frequency analog RF applications. And there we've seen that the key figure of merit is the transconductance of the transistor. Now, if I use a simple square law model for the MOSFET and just take the derivative of the drain current with respect to the gate to source voltage, I could write that transconductance as drain current divided by Vg minus Vt divided by 2. If I do the same for the bipolar transistor, the collector current goes exponentially with emitter base voltage. When I do that derivative, I find the transconductance is collector current divided by Kt over Q. Now, some typical numbers, maybe a gate to source voltage of 1 volt, a threshold voltage of 0.2. Kt over Q at room temperature is 0.026. So if we compute Vg minus Vt divided by 2, we find out that it's about 15 times larger than Kt over Q. What that means is that the MOSFET transconductance is about 15 times smaller than a bipolar transistor. Or the bipolar's GM is 15 times larger. So, bottom line, bipolar transistors have a significantly larger transconductance, an order of magnitude or more. That's extremely useful for RF applications, analog applications. And in those applications, you'll see bipolar transistors used. By the way, you can trace that back to the fact that above threshold, the MOSFET current varies linearly with VGS. There really is no above threshold for a bipolar. All the way to high currents, the collector current varies exponentially with base emitter voltage, and that's what gives us the higher transconductance. So, the higher transconductance is advantageous for the bipolar, but both of them can have high speed because, as we saw earlier, the maximum frequency, the unity gain frequency, is transconductance divided by total capacitance. BJTs offer much higher transconductance, and that makes them suitable for high-power amplifiers, but they also have higher capacitance. So we can achieve similar speeds in MOSFETs because although they have lower transconductance, they tend to have lower capacitance as well. All right, so we're talking about bipolar transistors. Most bipolar transistors used today are referred to as HBTs. The H means a heterostructure bipolar transistor, a bipolar transistor made from more than one semiconductor. And the easiest thing to do is to make the emitter out of a semiconductor that has a wider band gap than the base. Now, what's the advantage of doing that? Well, if we look into this expression for beta that we showed earlier, we'll see that there's a ratio of intrinsic carrier concentrations there. And we remember from semiconductor physics that the intrinsic carrier concentration goes exponentially with band gap. The wider the band gap, the smaller it is exponentially. So if we account for that, we'll find that beta depends on E to the band gap difference over KT. So if the emitter is wider than the base in terms of band gap, that factor can be quite large. And that means that independent of these ratios here, we can still get a good high current gain. Now, why is that advantageous? Because that means that we can dope the base very heavily and make the base resistance very low, which is advantageous for transistor performance, but it does not degrade the gain because of this wide band gap emitter. Now, that wide band gap emitter means that the device is no longer symmetrical, and that can be a problem from time to time. So sometimes you'll find bipolar transistors that are called double HBTs. There's a wide band gap emitter and a wide band gap collector, and when you do that, the device is more symmetrical. So we get symmetrical operation. We don't get an offset voltage from the origin, which we can in the single heterojunction device. We can also get a higher breakdown voltage from the collector because it has a higher band gap semiconductor. So there are advantages in using double HBTs as well. So to summarize bipolar transistors, most bipolar transistors used these days are heterojunction bipolar transistors. 3,5 HBTs are an important technology for high-frequency RF power applications. Silicon germanium HBTs are a critical technology for wireless applications, and we use them in some of our personal electronic products like cell phones. HBTs and HEMTs can offer similar speeds. As I said, the HBT has much higher transconductance, but the HEMT can have much lower capacitance, and both of them are important for high speed. Compared to HEMTs, HBTs will deliver higher power and perhaps higher integration densities as well. But the takeaway here is that this is not a fundamentally different kind of transistor. This transistor also operates by controlling energy barriers with applied voltages to the terminals, and that control of the energy barriers controls the current and gives us the transistor characteristic. So the final topic that we discussed in this Unit 5, this unit, was compact circuit models. And we just very quickly made a few points, that they're the link between the designer and the manufacturer. They also are a link between people doing earlier stage technology development who need to explore what the implications of this new technology would be on circuits and systems to justify the development of that new technology. Developing a new compact model requires a good understanding of the device physics for the core model. It also requires an understanding of what goes on inside the circuit simulator and how it solves the circuit equations. And it also requires an understanding of the intended application so that you'll focus your attention on producing an accurate model for the aspects of the model that most influence the application that you are interested in. There's a lot of art and science to developing a good compact model. If you're doing it for a brand new device, I'd encourage you to spend some time looking at the history and what has been learned in the development of compact models for MOSFETs, because many of those lessons learned can be applied to novel devices as well. So that's what we did in Unit 5. We talked about fundamental limits of MOSFETs. We indicated how MOSFETs could be used in a quite different application and what the key figure of merit was for those power applications, the on resistance versus breakdown voltage trade-off. We briefly introduced a different kind of field effect transistor, the high electron mobility transistor. We also talked about a bipolar transistor, another type of barrier controlled transistor, but one that is quite different in some aspects. And we ended by circling back and saying a few words about compact models, specifically about compact models used by designers for sophisticated electronic design. So that's it in Unit 5, and that actually concludes the course. So congratulations for sticking with it. I hope you've learned some useful things about transistors that you can take with you in your career or your further studies if you're still a student. You know, we talked about some basics of transistors and rudimentary aspects of circuits in Unit 1. We presented a very simple way in terms of energy bands to understand the essential physical operating principle, not only of a MOSFET, but of any barrier-controlled transistor. We spent a significant amount of time in the most challenging unit, Unit 3, in which we took a look at MOS electrostatics, which is a critical aspect in the operation of a MOSFET. And then we talked about how a modern way to think about transport allows us to describe very short devices all the way to the ballistic limit, where 3,5 field effect transistors are today, the diffusive limit, where traditional transistors were for many, many years, and the quasi-ballistic regime where silicon MOSFETs operate today. And then we talked about a few additional topics in Unit 5. So, congratulations again for sticking with the course. I hope you've learned some useful things that you can take with you, and good luck on the final exam.